Good day. In this machine learning foundation project, I need to develop a predictive model for the electric energy output of combined cycle power plant CCP. We will leverage the models to train and predict the expected outcomes of the data features. Our feature ranges by feature type are as follows. The ambient temperature, AT, column A, has a range of 1.81 to 27.11. The exhaust vacuum has a range of 25.36 to 81.56. The ambient pressure, column C, has a range of 992.87 to 1033.30. The relative humidity, column D, has a range of 25.56 to 100.16. And then we have column E, PE, also known as PE, is our electrical energy output, which has a range of 420.26 to 495.56. For our training model, what I have done here is taking the particular models that we could leverage for a training model, such as a logistic or regression. I chose a linear regression. These models are easy to understand. I chose the linear regression because it works well in Excel and often is used as a benchmark for more complex models. The multilinear regression establishes the relationship between the independent variables, which are our features, and are used currently today to predict changes in the stock market, or in this case, the features such as temperature and humidity and the energy output for our power plant. The metrics that we will review today are the means, the absolute error, MAE, which measures the average magnitude of the errors between the predicted and the actuals. And if you notice in my graph here, I've plotted the predicted PEs along with the given PEs, and you will see that they are close and crunched together, meaning that most of the data features which have been provided are right on point. You will also see the R squared, which is 0.9296. This indicates that the portion of the variance in the dependent variables that is predicted from the independent variables. So basically, we're comparing and looking at the proximities. Next, you will notice that I've actually calculated the mean, the MAN, mean absolute error. And this is done, and I've actually provided the steps to do this. What we do is we actually tally the total absolute errors divided by the number of rows, and that determines our mean. In addition, we have our coefficients for each feature attribute, which takes into consideration. We have here in the regression stats, we have the multiple R, which is the coefficient of multiple correlations. We have the R squared, which is the outcome of the observed data, henceforth why everything is very close proximity on the graph. We have the adjustable R squared, which shows us how well the statistical data from our features fit based on the data set. And then the standard errors. I've also included the correlation factors to determine our percentages per feature. The ambient temperature is a negative 0.98. The exhausted volume is a 0.98. The atmospheric pressure is a 0.54. The RH is a zero point 0.5, and thus we get the actual PE of 0.96. This actually tells us that the ambient temperature has the largest negative impact. The ambient pressure has the smallest positive impact, and the RH and V both pull the output down slightly, and that will explain why you will see some of the feature points just outside the proximity there. For the variance, basically followed the same format, but we have a little tighter fit, if you will, in the actuals versus the predefined PE. And for the validation, you will notice that my mean is 3.66, the same data set, different values. The training module actually had 80%. The validation model had the remaining 20, and this is actually the standard when you're working within linear regression. And that's the end of my presentation. Thank you.